All right, let's just dive right in. We're about to unravel a really fundamental puzzle about our world, at the tiniest, microscopic level. We're going on a little mission to figure out why molecules, the building blocks of literally everything, have the very specific shapes they do. And trust me, this is a mystery that defines pretty much everything. And our whole investigation kicks off with a question that sounds so simple you've probably never even thought to ask it. Why is a water molecule bent? It just seems kind of random, right? But as you're about to see, there's a really beautiful, elegant logic behind it all.
Now check this out. This is where it gets really interesting. On one side, you have water, H2O. On the other, carbon dioxide, CO2. Both are made of just 3 atoms. And yet, look at them. Water has this funky bent shape, while carbon dioxide is just a perfectly straight line. So, same number of pieces, but a completely different final product. What is going on here?
To solve this little mystery, we have to look at the blueprint. And in the world of chemistry, the blueprint is always about the electrons. If we can figure out where the electrons are hanging out, that's our first major clue to understanding the final shape. Okay, so not all electrons matter for what we're doing. We really only care about the ones on the outermost shell of an atom. They're called valence electrons. You can think of them as these social electrons. They're the ones that actually do the work of connecting and forming bonds with other atoms. They are absolutely the key players in our story. So how do we actually map out where these electrons are? Well, we use something called a Lewis structure. It sounds complicated, but it's just a simple 4-step recipe. First, you count up all the valence electrons. Easy enough. Second, you figure out which atom goes in the middle. Third, you connect everything together with some basic bonds. And finally, you just sprinkle the rest of the electrons around to make sure all the atoms feel stable and complete. And boom, you've got your blueprint. Okay, so we have our 2D blueprint. Now we need the rule book, right? The thing that tells us how to turn that flat drawing into a real 3D shape. And luckily, there's a powerful theory that is basically the golden rule for all of this.
And here it is, VSEPR theory. Yeah, I know, it's a mouthful. Valence shell electron pair repulsion. But forget the fancy name, because the idea behind it is incredibly simple. It just says that electrons are going to push each other away. They want to arrange themselves to be as far apart from each other as possible. It's kind of like when you get into an elevator with a few strangers. Nobody huddles on the corner, right? You all instinctively spread out to maximize your personal space. Electrons do the exact same thing.
And that is the whole game, right there. It's all about personal space. Since all electrons have a negative charge, they naturally push each other away. And VSEPR theory basically says that this constant pushing and shoving is the only thing that really dictates the molecule's final 3D shape. It's that simple. And this table is basically our VSEPR cheat sheet. It's the key to everything. All you do is count the number of electron regions around that central atom. And this is important. That includes both the bonds and any extra pairs of electrons just sitting there. Once you get that number, the table just tells you the shape. See? 2 regions, they get as far apart as possible, 180 degrees, making a straight line, just like CO2. 4 regions, that gives you a perfect tetrahedron. But here's the twist. Look at those last 2 rows. When some of those regions aren't bonds but are lone pairs of electrons, the shape we see gets a different name, a name like bent. All right, we have our blueprints, we have our rule book. It is time. Let's go back to that original mystery and finally solve this case once and for all. Why is water bent? Okay, so we draw the Lewis structure for water, our blueprint. And what do we see? A central oxygen atom connected to 2 hydrogen atoms. Looks pretty simple. Based on this alone, you might guess it would just be a straight line. But that would mean you're missing the crucial clue. And here it is, the smoking gun. After the oxygen atom makes its 2 bonds, it still has 2 extra pairs of electrons just hanging out. These are called lone pairs. And even though they're kind of invisible in simple diagrams, they are absolutely there. And boy, do they take up a ton of space. So let's do the count. We have 2 regions from the bonds connecting to the hydrogens, plus the 2 regions from those invisible lone pairs. That gives us a grand total of 4 electron regions, all crowded around that one central oxygen atom. And now we go back to our rule book. We look at the cheat sheet, and what does it say for 4 electron regions where 2 of them are lone pairs? It gives us one result and one result only, a bent shape. It all makes sense. Those 4 regions all push on each other, and the powerful lone pairs shove the 2 bonds down, creating that famous shape we all know. Case closed. And this just explains the original puzzle perfectly. Water is bent because its oxygen has 4 electron regions all fighting for space. Carbon dioxide, on the other hand, is a straight line because its central carbon only has 2 regions, the 2 bonds it makes and 0 lone pairs. With only 2 things to keep apart, the best way to do it is a 180-degree straight line. It really is all about those powerful, invisible lone pairs. So great, we solved the puzzle, but why do we care? What's the big deal? Well, it turns out that a molecule's shape isn't just some fun fact for chemistry class. It is, and I mean this quite literally, it's everything. It defines what a substance is and everything it can do. For example, take a look at this idea of structural isomers. These are molecules that have the exact same recipe, the same atoms, same chemical formula, but those atoms are just snapped together in a different order, which gives them a totally different shape. And this is the main takeaway. A different structure means a completely different substance, period. You change the shape and you change everything. How it looks, how it reacts, how it smells, its function. You change its entire identity. In the world of chemistry, shape is function. So I'll leave you with this final thought to chew on. We just saw that for the smallest, most basic building blocks of our reality, their shape determines their entire identity. So the question is, where else is that true? I mean, think about it. From the shape of a key fitting into a lock, to the architecture of a skyscraper, even to the structure of entire galaxies. How much of our universe is built on this one simple, elegant principle? That shape is everything.